Hello everyone, my name is Xavier. I'm a PhD candidate at Université de Sherbrooke, liride. Today I'm presenting to you some preliminary results on the development of a computational framework for measuring the sustainability of natural hazard resilient cities. This is the outline of the presentation. To give you a little bit of context, providing cities with a resilient built environment to mitigate the effects of natural hazards which are actually uncertain to happen while also optimizing sustainability is challenging. That is, they are both design objectives. They might actually yield trade-offs between one another, and yet measuring the environmental impacts of resilience is kind of challenging in itself. Another point to bring up is that this project is not the first one to look into measuring the sustainability of natural hazard resilient cities. There's already been work in that direction where essentially it is broken down into 4 steps. One of them is measuring the hazard on site, how the structures respond to this, then moving on to what are the damages entailed, to figuring out how to repair the structures and thus define the amount of environmental impacts associated with these repair activities. It should also be noted that while the discussion is going to be mainly focused on one singular hazard, this framework can always be adapted to other types of hazards, such as flood-related hazards, fire-related, wind-related, or ground-related hazards. The research gaps that this project aims to tackle are that current frameworks and tools enforce technical limitations to LCA. That is, for example, simplified lifecycle inventory modeling, where it is not possible to modify the data sets or even have access to process-based LCA. It's also to have access to other modes of LCAs beyond attributional mode of LCA. So that is, for example, having access to consequential LCA in modeling resilience needs. If we're going to also move into more advanced LCA, it would be interesting, for example, to use conventional generic LCA softwares, but they tend to become much more cumbersome when it comes to interoperability. That is, moving all these data that comes from the previous assessment steps into the LCA in itself is very challenging, and it's very data intensive to bring in this information into the LCA. So the objective of this research is to develop a computational framework that will really improve on these 2 points and give access to modeling natural hazard-induced environmental impacts for resilient cities. The framework we're proposing essentially builds on previous work by using the same building blocks, where it starts with defining a hazard curve that requires the intensity of the event and the probability of these individual events, so the mean recurrence interval. It then goes on to connect this hazard with the structural modeling, so floor per floor, what is the behavior of the building, and then we're going to investigate what is damageable in the building and to what level. So say, for example, is the element not damaged, or is it has minor damage and requires minor repair? Or, for example, in the pictogram, we have this red window that is essentially a window that is totally broken and will need to be completely replaced. Now, knowing these damageable components can run into the damage analysis, which will actually now enable us to start investigating what needs to be repaired, how it needs to be repaired, and get our environmental impacts associated with this. Now, there's also an alternate way to see this. Instead of going component per component in the building to define the environmental impacts, and it can be interesting to go at the whole building scale, at the whole structure perspective, where we're going to instead take a set of buildings and define whether they are minorly damaged, moderately damaged, or in severe damage and need to be replaced, for example. Now, obviously, for the perspective on a city scale, we're going to follow rather the perspective of the whole structure perspective for the size of the assessment because of numerous buildings it involves. Now, for our specific case study today, we're actually following buildings in neighborhood in the city of Halifax, Canada, where we derived a hazard curve for a hurricane in this neighborhood. The next step is to discretize the hazard curve into 18 bins or 18 wind speeds and find the associated likelihood for each of these wind speeds. And then we connect this with 20 buildings that were taken from Brels. Brels is a near sim center software that goes essentially on Google Street View, and for the location we give it, find all the buildings in the area and try to find some features on these buildings, such as the number of stories, for example. Now, obviously, we're not going door to door to verify the structural detailings of all of these buildings, but the framework is also able to account for this type of uncertainty by assigning more than one archetype per building and flipping between these during the simulations. Once we have the wind speeds and the buildings, we can actually send in, for example, 10,000 simulations per wind speed to get a good feel on what are the expected damages this neighborhood will sustain under these different wind speeds. Now, for demonstration purposes, we're going to look at the damage states according to the wind speeds, and we're taking a sample of 3 wind speeds. So one on the far left is going to be the lowest wind speed we can have in the model, while on the far right, we're taking a data point that is the highest wind speeds we might get, and something in the middle to get a sample of damage states for demonstration. Now, these are the damage states that we get for a wind speed of 56 miles per hour. We essentially get no damage on the buildings, while at the bottom of the slide, we get a wind speed of 211 miles per hour, and where we see that all the buildings are essentially damaged in damage state number 4. Damage state number 4 essentially corresponds to the buildings are collapsed or in need of immediate replacement. And we see just in the middle, wind speed of 148 miles per hour. In this case, instead, we get a mix between damage state 1 through 4. And that's the interesting part of it, because that means that the simulation can actually provide us with buildings that are going to be instead in a mix and match between all these these damage states for the wind speed. And it can be also yielding that buildings that are not damaged, buildings that are only having a minor roof damage, a major roof damage, or a collapse situation. With all these thousands of simulations, we're now ready to move these damages into the LCA part of it. For this purpose, we developed a Python library that automates the meshing between the natural hazard damages and the LCA datasets. Essentially, it takes all the potential damage state that exists and creates empty datasets that we're actually filling in with eco-invent datasets, and then automatically takes care of the rest into mapping the simulations and the resulting damages that we get in each individual simulation into a Monte Carlo simulation. And the underlying background engine is Brightwave. With this, we now have what it takes to actually connect the damage state simulation with individual Monte Carlo simulations that are corresponding with the scenario that we got. And these are the results for the 3 wind speeds we were looking for earlier. So for the climate change 100 years, the ecosystem quality and human health of impact world plus indicators, we get that 56 miles per hour of wind speed yields close to no environmental impacts. At the other end, we get at 211 miles per hour very concentrated results that are essentially stacked up on high environmental impacts. And just in the middle, 148 miles per hour, we get a less concentrated distribution of environmental impacts due to having a mix between damage state 1 all the way to damage state 4 mixed up in this result of wind speed. And this brings us to the overall framework. However, what is interesting to do with this framework is essentially to look at the expected annual losses here. So if we're looking at this slide here, for example, on the left of the chart, we get higher probabilities of having almost no environmental impacts, while we get very low probabilities of having very high environmental impacts. Now, that is because we are actually factoring in that all these wind speeds, these 18 wind speeds, have different likelihoods of happening. And this enables us to integrate all of this into this single curve here. And the most interesting part of this is to do the area under this curve here, and that's where we get the numbers on the top right of the graphs. And this can be read essentially as, when we integrate this, yearly, the hurricanes are expected to contribute an additional 3.5 tons of CO2 equivalent to the environmental impacts of these 20 buildings. And what's interesting with this framework is that it improves the access to comparing environmental burdens stemming from numerous scenarios of resilience independently of the size of the city. So in conclusion, this project proposes a new framework enabling access to advanced LCA. It is able to be upscaled to the size of cities, and it allows to investigate numerous scenarios of resilience. The upcoming steps would be to demonstrate the framework applicability at individual building scale, so going at the size of components by components in an individual building, and to investigate the feedback effects of climate change on total environmental losses. Before I go, I want to just give a quick shout out to the funding agencies for this project. And if there are questions and comments, I will be happy to answer them at the end of the session. Thank you.